the area between the x-axis and the curve y equals sine 2x. So the graph of the sine function looks like this. Right, that's one period of the sine function. But the graph of sine 2x, what is its period? Pi, yeah, because the period is 2 pi over b, b being the coefficient in front of the x. Remember this from pre-calc? So the period here would be 2 pi over 2, which is pi. So that means that this is pi. This is pi over 2. And then what I want is the area from 0 to 2 pi. So I have to graph a second period. And I want to find all of this area between the curve and the x-axis. So this, and this, and this, and this. So if I just took the integral from 0 to 2 pi of sine 2x, what would I get? 0, because there's the same amount of area above the x-axis as below the x-axis. So my net signed area would be 0. But if I want the total area, don't think about signed area, just the amount of area that I just shaded. How would I find that? Sure, each of these arches has the same amount of area. So if I just integrate from 0 to pi over 2, and multiply that by 4, because I have 4 arches, that'll give me the area. And we don't have a lot of techniques for finding integrals by hand, so I'm going to use my graphing calculator. So that's in the math menu, fint. We put the function first, sine 2x, and then comma x, and then that's just telling it that x is the independent variable. And then we have to put in the bounds of integration, 0 and pi over 2. And it looks like the area under each arch is 1, multiplied by 4. 4 times 1 is 4. Does that make sense? Okay. All right, so again, I've included a bunch of challenge questions throughout the packets. So whenever I ask you to work on something individually or in your groups, there's usually a challenge question or questions that if you finish the first thing, you can work on those. But they are a real challenge usually. So if you don't get them, it's not a big deal. And we probably won't spend time in class talking about them. It's just so you have something to do if you finish early that will extend your understanding a little bit. All right, so here is a graph, and we want to talk about approximating the area under the curve using a left-hand sum. On what interval would the left sum be an overestimate? So maybe we should just draw in the left sum for the whole graph. So that means that on each interval, we're going to use the height of the graph on the left side to make a rectangle. Remember this? So from -2 to -1, I use the height of the graph at -2 to build a rectangle. All right, so where in this graph, what interval of x values are those rectangles overestimating the area under the curve? 0 to 3. Yep, 0 to 3. Okay. So the reason that those are an overestimate is because this function is decreasing. When the function was increasing, the left-hand sums were underestimates. All right, quick refresher on definite integrals. If you have a continuous function f of t, and for now we're going to assume that it's always positive, but all of our conclusions do extend to when functions are negative also. We're looking for an estimate of the area under the function from x equals a to x equals b, and you can estimate that area using rectangles. We're going to let v equals f of t be a non-negative function on the interval a to b. We cut it into n equal pieces, which give us a set of equally spaced t values, t0 to tn. And this picture came out terribly. Let's see. So this point right here is a, which is also t0, and then we have t1, t2. So we're just breaking up this interval from a to b into n equal pieces, t0 to tn. So this point right here, sorry, this point would be t sub n minus 1. All right, so to approximate under the area under the function by a left-hand sum, over each interval I have to build a rectangle, and I determine the height of the rectangle using the height of the function at the left end of the interval. So from t0 to t1, I would build a rectangle. There's my base. The height is going to be determined by the height of the function at the left endpoint, and I build a rectangle there. And then t1 to t2, I do the same thing. And then tn minus 1 to tn. Yeah. So those are that's my left hand sum. And each of those rectangles has a width delta t, and then the height is a function value. So my function values start at t0 and finish at t sub n minus 1. That's my last height that I use when I do a left-hand endpoint. So that's why I have an f of t0 and an f of tn minus 1. All right, and then when I do right-hand sum, over every interval, I'm going to build a rectangle that has the interval as its base, but then we determine the height of the rectangle by the height of the function at the right-hand endpoint of the interval. So here's my interval t0 to t1. To determine the height, I'm going to use the right-hand endpoint of the interval. And so then for this last interval, I would use b, or t sub n, as my last height. And each of these rectangles has width delta t. So that's where all these delta t's come from. And a height that's a function value. And the first rectangle, its height is f of t1. We find the height by the function value at t1. And the last rectangle, its height is found by f of tn. So this one starts at t1 and finishes at tn. All right, we abbreviated these sums using sigma notation. So for the right-hand sum, the second one here, the right-hand sum, it's always delta t times f of t sub something. And it starts at the sub things, the subscript starts at 1 and finishes at n. So to write this in sigma notation, you put a big sigma, and then I would say delta t times f of t sub I, and we have that I be my something, and then we have I starts at 1 and finishes at n. So that's the sigma notation for that long sum. So then I've got some pictures here that demonstrates the more rectangles you use, n is the number of rectangles, so the more rectangles you use, the better approximation you get of the area under the curve. So what we do is we let this n, the number of rectangles, go to infinity. We take a limit as n goes to infinity, and that tells us the exact area under the curve, this limit. And then we said, well, this notation is really cumbersome. I don't want to write this down all the time. So we said we're going to let this limit mean the same thing as this. that elongated S stands for a sum, an infinite sum from A to B. F of t represents this f of t sub I, and dt represents that delta t. So that's where the dt notation comes from, and it's really easy when we're getting sort of bogged down in the techniques of integration to just say, oh, that dt doesn't mean anything. And you do kind of ignore it sometimes when we learn new techniques, but it does mean something, right? It means the width of the rectangles that you're taking the limit of under the curve. All right, so this symbol, the integral from a to b of something dt, is called a definite integral. The numbers at the top and the bottom, the a and b, those are called the limits of integration. And the function that you're integrating is called the integrand. All right, so imagine that this picture that has regions 1, 2, and 3. Those have areas 4, 10, and 7 respectively. What is the integral from 0 to a of f of x dx? 4, just the area under the curve, right? And what's the integral from a to b? Yes, -10. The area of region 2 is 10, but because it's under the x-axis, we give it a negative value. All right, how about from 0 to c? One. 4 for region 1, -10 for region 2, plus 7 for region 3. So that comes out to a net area of 1, +1. What about the integral from c to a of f of x dx? 3, -3. Right, so from a to c, if I was going to do the integral from a to c, because we always do these things from left to right, then I would say, well, this is -10 plus 7, which is 3, right? But how do you translate that to mean, what does the integral from c to a mean? Well, how is it different from a to c? Oh, it's -3. Yeah, this is -3. Thank you. Anybody remember? You just change the sign. Yeah. You can think of it, if x were time, then if you go from c to a, it's like you're going backwards in time. And so you're, and this thing represents displacement, right? The integral, if this is velocity, this -3 would represent displacement. And if this was c to a going backwards in time, your displacement is just like the opposite, +3. So limits of integration always go left to right. If you switch them, you can just go left to right, but then take the opposite sign. All right, then one of the last things we talked about last semester is the fundamental theorem of calculus part 1. It says if f prime is continuous on a to b, then the integral from a to b of f prime of t dt, okay, so if you take the integral of a derivative, that's equal to f of b minus f of a. And in English, this says the definite integral of a rate of change, right, because a derivative represents a rate of change. So this says the definite integral of a rate of change is total change. Right, so f of b minus f of a tells you the net total change in the function f. So if you think of it as velocity, when you take the integral, which is the area under the curve of a velocity function, which is derivative of position, your units on the rate of change would be, say, I don't know, something like meters per second. Your units on dt, which is the width of your rectangle, would be the time units, which is seconds. And these would cancel and you'd get meters. And then f, your position function, would also be measured in meters. So an integral of a rate of change is total change. All right, so I have the velocities of two cars. These are their speeds. Assuming that the cars start in the same spot, you can see that car 1 starts out going much faster than car 2. At 1 second, they're going the exact same speed. Can we figure out when car 2 overtakes car 1, when it catches up? Or that is, when they have traveled the same distance? Yeah, we got to figure out at what point the areas under the curves are equal. Right, so take a few minutes and see if you can estimate. It's definitely going to be an estimate because you don't have perfect values on this graph, but see if you can figure out approximately when the area under car 2 equals the area under car 1. At what t-value? All right, so we've had a proposal of about 1.5. Okay. So if you look at the area under car 1 from 0 to 1.5, that would be this pink shaded area here. And we could try to estimate what that is, right? Just by counting these boxes. Even though each box doesn't actually represent 1, we could just count the number of boxes and see if it's approximately the same as the area under car 2, which would be this. So the pink area and the blue area, they share a lot. They have a lot in common. So if we just look at the part that's strictly pink and the part that's strictly blue, those look approximately the same. They're pretty close. So it does look like it's somewhere between 1.25 and 1.75 at about 1.5. All right, so we have a graph of f prime. So this is the graph of the derivative of f, not f itself. We want to find the integral from 0 to 4 of f prime of t dt. How do we do it? All right, you guys can. All right, so the integral from 0 to 4 of f prime of t dt means the area under f prime between 0 and 4, the net signed area. So I can break this into regions that it's possible to use a geometry formula, like the area of a triangle, to figure out the area, right? So we've got this one here. And this is a triangle. My base is 1, my height is 2. So what's its area? 1. 1/2 base times height. Right? So it's got an area of 1. All right, and then this region, it's got a base of 2 and a height of 1. What's its area? 1. 1/2 base times height again. So this whole thing has area 1. Well, it's -1 because it's below the x-axis. And then this last piece, that triangle has a base of 1 and a height of 1, so its area is 1/2. Yeah. Okay. So my net signed area under the curve would be 1 minus 1 plus 1/2, which is 1/2. Everybody get 1/2? Okay. So now, if f of 4 is 2, we're supposed to find f of 0. And we're going to use the fundamental theorem of calculus to figure this out. So we know that the integral of a rate of change is equal to the total change. So the integral from 0 to 4 of the derivative is equal to f of 4 minus f of 0. And now I know the integral from 0 to 4, because I just did it, is a half. And they told me f of 4 was 2, so I can now solve for f of 0. So if I subtract 2 from both sides, I'd get negative 1.5. So f of 0 is 1.5. Make sense? All right, in your groups, I want you to figure out what each of these definite integrals represents. So to make life easier, remember that the units for an integral are the product of the f prime units times the product of the t units, the dt, right? So this is f prime units times dt units, multiply those together, and you get the units for the whole integral. All right, let's talk about the meaning of these three integrals here. So when you're finding the area under a velocity curve, what are you actually finding? Displacement or position, yeah. So in any case, you could say, oh, well, my units on v of t are kilometers per second, and my units on dt are seconds, because dt is a small change in time. Your seconds cancel, and you get kilometers. Right? So you know that whatever this thing means, its units is kilometers, and then you can work backwards to say, oh, what do you measure with kilometers? Position or distance or displacement. So what do the 0 and the 120 represent? Seconds after launch, right? So this integral represents distance traveled in kilometers, 120 seconds after the launch of the rocket. All right, so for B, A of t gives the rate in thousands of antibodies per minute. And dt is a small change in time, so that would be minutes. So this integral is measured in thousands of antibodies. And 0 to 4, what does that represent? What do the 0 and the 4 mean? They're minutes, measuring what? Time after the substance is introduced. So from t equals 0 is when the substance was introduced. So 4 minutes later, we can count how many antibodies are in the blood. So this is the number of antibodies in the blood 4 minutes after the substance is introduced. Okay, so the next one, R of t, is the rate in millions of dollars per year. And dt is a small change in time, so its units are going to be years. Years cancel. So this represents millions of dollars. So the integral from 1980 to 1990, those are years, right? Year t, 1980 to year 1990. What do we, how do we interpret this integral? Total change in debt measured in millions of dollars. From 1980 to 1990. And it would probably be an increase, right? Probably be an increase in the debt. Okay, so there are several challenge problems that you can continue to work on. Or if you'd rather, you can have almost all the information you need to do project 1, except possibly for number 11. And even number 11 you might be able to do if you think about it hard enough. So if you want to work on that, you can work on that too.